Now we use our electron configurations to think about periodic properties, and big ones in A level, atomic radius or size, and then of course the ionization energy. So let's do a few. We'll start with size, looking at the periodic table because this is a periodic property. The size increases as you go down a group because you're going to increasing shells, and the shells get bigger as the shell number increases. And then as you go from left to right, the size decreases because you have the same shell, so the same level of shielding, but increased nuclear charge. Now let's look for our first one. Of course, the first trick with the first one is that we want it in increasing size, and they've got it in decreasing size. But as we go through, selenium is indeed bigger than silicon, but antimony here is certainly not bigger than bismuth. Bismuth is bigger than antimony. So even though it's in the wrong order, we also have a wrong relationship in there anyway. Let's go to B. So we got cesium, strontium, lead, and iodine. Well, let's see. Cesium down here is probably going to be the biggest element on the table because it's the furthest down and the furthest to the left. So I would say that cesium is bigger than strontium, not the other way around. Cesium, calcium, rubidium, strontium. So let's add on rubidium and calcium here. Well, again, cesium should be the biggest. It's actually listed here as being the smallest, so that's definitely messed up. Bromine, strontium, barium, cesium, let's add those in. Well, let's see. Bromine all the way over here, it's the furthest up, which would make it the smallest, the furthest to the right, which would make it the smallest. So bromine, definitely the smallest. Then as we go here, I would say strontium is the next. Strontium is going to be smaller than barium. Barium is going to be smaller than cesium. So that looks pretty good, doesn't it? But let's check just to make sure that the last possibility is also wrong. So that we're throwing in calcium. Calcium should be the smallest, but then it should be strontium, barium, cesium. Instead, you've got cesium stuck in there in the second place, so that's the wrong way. So again, went through this slightly more lengthily than otherwise might have been the case, but just to show you how we're thinking. So anyway, D is the one with increasing size. Now we look for decrease in atomic size. Again, let's look through them. So what we've got here is we want decreasing. So in other words, we want to start with the biggest and end with the smallest. This has the signs in the right way, but of course sodium is actually the smallest of these. Cesium is the biggest. So it should be cesium bigger than rubidium, bigger than potassium, bigger than sodium. Now let's look fluorine, nitrogen, boron, beryllium. So we want decreasing, we want to start with the biggest. So beryllium will be the biggest, then boron, nitrogen. So again, those are flipped in order. Now we've got replacing carbon in there. So we've got beryllium is the biggest, boron, carbon, nitrogen, boron and beryllium switched around there. And now finally, as our options, CNOF, biggest is carbon, then nitrogen, then oxygen, then fluorine. That is indeed carbon, nitrogen, oxygen, fluorine, the right direction. So excellent. Now we move to ionization energies, and ionization energies are effectively the reverse. So as we go down a group, we see those decreasing, and that's because of increased shielding, at least at the A-level explanation. And as we go across a period, the ionization energy increases because again we have the same level of shielding, if you like, increased nuclear charge, which means that the nucleus holds more tightly to the electrons as you go from left to right, thus making it harder to pull away the electrons. So let's put in our little series here. First of all, I'll dump E out the way because I want increasing, and this has got the signs of decreasing, regardless of whether or not it's the right order. We want it to be smallest at the start and biggest at the end if they're increasing. Now let's look at sodium, strontium, oxygen, fluorine. We'll work backwards here. Well, what I would definitely say here is strontium is really low down, so that's probably the smallest. Then it would go sodium, then oxygen, fluorine. So I would say that the sodium, strontium order is messed up. Now, all of these A, B, and C have the same atoms, right? Lithium, nitrogen, oxygen, fluorine. Well, this one here, Fluorine is less than oxygen, less than nitrogen, less than lithium. That's going the wrong direction, so that's flipped. And what we would expect here, of course, is it goes lithium, nitrogen, oxygen, fluorine. So that would imply that B is the right one. But you might remember, and indeed you need to remember, because the A-levels really like setting questions on this, that this going from left to right increase is not a smooth increase. It's a little zigzaggy bit. So lithium is fine, it's smaller than beryllium, but then beryllium's bigger than boron because beryllium represents a filled S subshell. So harder to remove an electron from a filled S subshell. Boron is lower than it should be because when you remove an electron, it makes a filled S subshell. Same flip for nitrogen and oxygen. Nitrogen is actually bigger than oxygen. Nitrogen half-filled P, breaking into that is tougher. Oxygen, when you remove an electron, you make a half-filled P, which means it's a smidge easier than should be. So important that you remember that, right? Beryllium and boron switched, magnesium and aluminium switched, and then we get up halfway through the P, nitrogen and oxygen switched, and in the next period, phosphorus and sulfur switched. So the actual answer here is A. Lithium, no doubt, is the smallest, fluorine is the biggest, but oxygen and nitrogen switched in the middle. Second ionization energy, so that's removing a second electron. Well, in any set of ionization energies, the largest value is that associated with removing an electron from a noble gas configuration. So noble gases have the biggest first ionization energy. But the second ionization energy, as I said, is after one electron has gone. So after one electron has gone for the alkali metals, then you've got a noble gas configuration, which means now you don't need to remove that second electron. It's really tough to do it. So what we're looking for, the alkali metals, we have rubidium, we have potassium, but of course potassium is above rubidium, so therefore it has higher ionization energies generally. So potassium is the answer here. And now, same kind of idea. An atom has the following ionization energies: 800, 2,500, 3,500, 25,000. So we see a massive jump from the third to the fourth. So in other words, after we've removed 3, that means now we have the noble gas configuration. So trying to remove a fourth one is breaking it from the noble gas configuration, much tougher. So we want something that when it loses 3 electrons is a noble gas configuration. Lithium loses 1, boron would lose 3, nitrogen have to lose 5, oxygen would lose 6 to get to a noble gas, and of course neon is a noble gas, so that means its first ionization energy is its big one.